Just
yeah, so this was just the compromise.
But thank you for pointing that out.
everyone. Well, you can continue with the talk.
Okay.
Check.
Yes,
It's splashed on the screen.
Oh.
Yes. So once again, we consider first this very weak kind of convergence for the convergence distribution for random variables, which simply says that the moments of a n converge to the moments of a as n goes to infinity. Tau of a into the k converges to tau of a as n goes to infinity. And now a little reminder. Remember that the Cauchy transform associated with A, it's a formal power series, formal power series GA of Z, which is sum of tau of A to the K divided by Z to the K plus 1. And A is a formal inverse of this power series at infinity, which is written as 1 over Z plus sum of CK Z to the K minus 1, or 1 over Z plus the R transform. To deserve this. There's something wrong. Something is wrong.
Frozen. Oh, can I try it now? Yeah.
Okay, very good. Thank you. Yes, CK, which is also denoted CK of A. Actually, I'm not sure this is the traditional notation for it. This is the kth free cumulant of A. And here are a few examples of these things. The moment cumulant formula that Andu was talking about yesterday applies in this case as follows. Tau of A is C1, tau of A squared is equal to C2 plus C1 squared, tau of A cubed is C3 plus 3C1, C2 plus C1 cubed. And then you can reverse calculate these things. C1 is tau of A and C2 is tau of A squared minus the square of tau of A, which you recognize as the variance of the variable, and so on. And it's very easy to see from these formulas that you have convergence in distribution if and only if you have convergence in cumulants. AN converges to A in distribution in this weak sense if and only if the cumulants of AN converge to the corresponding cumulant of A. Okay, so that's what convergence of distribution is. And one more thing that is good to know is how the functions G and how the cumulant scale when you multiply the variable A by the complex number lambda. And you have this formula which tells you that G lambda A of Z is equal to 1 over lambda times GA of Z over lambda, which is verified by that little calculation which I have written out, and which I'm not going to read. And this one, if you take inverses, amounts to saying that K lambda A of Z is equal to lambda K A of lambda Z. And this amounts to saying that CK of lambda A is equal to lambda to the KC K of A. Again, something that Andu we'll talk about a little more, but this comes from the multilinearity of the more general talking about. Okay. So now let's see what we can do with this. Suppose that you have a sequence B1, B2, which are free and identically distributed, short FID, and denote by AN the averages of these variables. And let's see what we can say about these variables. The kth cumulant of AN is 1 over n to the k times the k cumulant of B1 plus B2 plus Bn That's the scaling property that applies. Now you apply the additivity together. This is 1 over n to the k times n times ck of b1, or 1 over n to the k minus 1 ck of b1.
The identity distributed.
ck of bn is equal to ck of b1. This converges to 0 except when k is equal to 1, which is weak convergence of these variables to a variable whose cumulants are, first cumulant is equal to the first cumulant of b1, and all the other cumulants are equal to 0. So this is what I would call a very weak law of large numbers. Very weak because the convergence is very weak. It's convergence in moments, or formal, if you want, formal convergence. So
Cumulus of
something.
Now let's look at central variables. So let's say that we have again a sequence Pn,
Which is free and identically distributed, but this time the expected values are equal to 0, and the expected value of the squares are equal to 1. This from the formulas, from the moment cumulant transformation, you see that the cumulants are such that the first cumulant of b1 is equal to 0 and the second cumulant of b1 is equal to 1. And let's look at these weighted averages instead. b1 plus b2 plus bn divided by the square root of n, and do the same calculation that we did before. It's pretty much the same calculation, except that the scaling is by the square root of n instead of by n. So this is what you get there. So ck of am is 1 over n to the power k over 2 minus 1 ck of b1. And you notice that for k equals 0, that wants to blow up because I get things right. Yes, when k is equal to 0, that I'd like to blow up, but the ck of b1 is equal to 0. So that one stays equal to 0 all the time. But the second one also stays constant at 1, and the other ones go to 0 as n goes to infinity. And this leads to Voiculescu's central limit. It's also a weak, very weak central limit theorem, but it's a central limit theorem. Tells you that an converges weakly to the standard semicircular law. So that's why this is called the free Gaussian sometimes. I will return to both of these theorems. So these are, I promised at least one proof per lecture, and here we got 2 today. And I think I have a third one as well.
Okay. Now
Let's focus on the self-adjoint case, because that's a little more interesting. Because in this particular case, you can talk about the weak convergence in a more precise sense of the weak convergence of probability measures rather than just of moments, which of course doesn't exactly overlap, but it's more general and it's more concrete if you want. Distributions of self-adjoint linear transformations, in other words, unbounded self-adjoint operators, are simply Borel probability measures on the real line, which I will denote by a script P, so that I have a notation for it. The R transform is no longer a power series, because generally speaking, you don't have moments or cumulants for a probability measure defined on the real line. But let's look a little bit more carefully at what happens, what these transforms turn to in the case of probability measures. So first of all, the Cauchy transform is well defined. It's not a real number. G mu of z is the integral of d mu of t over z minus t, and it turns out to be convenient for a number of reasons to consider the reciprocal Cauchy transform, 1 over G mu. F mu is a reciprocal. And the reason for this convenience, one of the reasons is that the angular limit as z goes to infinity of F mu of z over z is equal to 1. So for instance, if you go to infinity along the imaginary axis, that limit is going to be equal to 1. But you can go in other directions as well, just not tangentially to the real line.
So
In other words, f mu of z can be written as z plus something, h mu of z, where h mu of z is equal to little o of z as z goes to infinity. So h mu of z, the dominating term is z. And this implies that if you restrict the function f mu to the angle gamma alpha, so which is an angle, it's an angle at zero, but it's also an angle at infinity, if you want. Conformally speaking, it's an angle at infinity. Then the function f mu is going to be actually invertible in that invertible conformal.
in such a gamma alpha, provided that you restrict yourself to
Large values of
what? And its inverse is going to be
z plus r mu of 1 over z, where r mu of 1 over z is going to be approximately minus h mu of z as z goes to infinity non-tangentially. So this squiggle that I'm going to use several times means that the two functions are asymptotic as z goes to infinity.
Is this obvious right away? So you can function which is identical plus
Something small relative to identity, and I'm saying that the inverse is z minus that same thing, right? So the function f moves you in the direction h mu of z a little bit, and the inverse is going to move in the opposite direction. H mu is a continuous function; it's an analytic function. So asymptotically speaking, you've got that going for you. Okay.
the linearization of the result.
As I pointed out yesterday, still remains correct. The R transform of mu1 pre-convolved with mu2 is R mu1 plus R mu2. For 1 over z and the gamma alpha with large imaginary part. And I'm going to call this function R of 1 over z. I'm going to call it phi because it saves on ink. Maybe 2 symbols. We save 2 symbols. Phi mu of z is R mu of 1 over z. Okay.
Scaling also works in this case.
And the weak convergence of probability measures, of course, is a more delicate concept, is a more interesting perhaps concept when you look at probability measures. A sequence mu n of probability measures tends to mu if the integral of every bounded continuous function f relative to mu n converges to the corresponding integral relative to mu. Or equivalently, mu n of an interval, let's say from a to infinity, tends to mu of a infinity for all values of a, except perhaps countably many exceptions. Okay. Again, I'm talking about things that everybody here knows, but let me not stress those things too much. Tightness also is a concept that probably you know. Tightness is the concept of relative weak compactness. Yeah, so because the real line is not a compact topological space, Borel probability measures do not form a compact set. You know, it's an
unfortunate thing, you know, masses
can go off to infinity, so to speak. And to make sure that you have a relatively compact set, you have to make sure that the masses don't appear at a great distance, right? So mu n for every epsilon there exists a t, such that most of the mass of the measures in the family or in the sequence mu n is concentrated in the interval from minus t to t. Okay, so that's tightness. This concept of tightness translates into properties of the functions phi mu, which I'm going to write here. These are kind of standard things that you do in classical probability theory. I think they go under the name of Levy's characterizations of weak convergence. That's it can be done in terms of Fourier transforms. It can also be done in terms of these functions phi mu, which are a substitute for the Fourier transform. Phi mu n is tight precisely when the phi mu n have a common domain of definition. So there exists some truncated cone where all of the phi mu's are defined. And also the fact that phi mu is little o of z is uniform over the sequence mu n. Okay. And mu n tends to mu if it's a tight sequence, and in addition, phi mu n converges to phi mu of z for z in some open set. Actually, any set with an accumulation point is enough for the convergence. Okay. Now let's see what the angular asymptotics are for the for phi mu. So remember, the phi mu is approximately z minus f mu of z. It's not equal, but approximately equal. And
Here's the little calculation, which I'm very fond of.
So you look at z minus f mu of z. This is z minus 1 over g mu of z. You do a little bit of algebra and see that z g mu of z minus 1 over g mu of z, which angularly speaking is the same as z times z g mu of z minus 1. Because g mu of z is about 1 over z. So this is exactly z times the integral over the real line of z over t minus 1, or the integral of zt over z minus t. And here comes a calculation, which everybody can check. Zt over z minus t, the integrand in that integral is constant, t over 1 plus t squared, plus 1 plus zt over z minus t times t squared over 1 plus t squared. I wanted to pause here a moment because this is a calculation which, as I said, is very easy to verify, but it took me 6 months to find. You know, so you have to realize that you need such an identity. And we'll see it in action in a moment. Okay. So now I want to come back to the weak law of large numbers and revisit it for the situation of measures on the real line. Excuse me. So the calculation that I just did just before tells you that phi mu is asymptotically at infinity expressed as gamma plus the integral over the real line of 1 plus zt over z minus t times d rho of t, where gamma is the integral of that constant that came constant as a function of z. Constant plus yes, okay. And the rho, the measure rho is t squared over 1 plus t squared times d mu of t. Okay. What I should emphasize here is that the right-hand side is the typical analytic function from h to minus h with the property that it is little o of z as z goes to infinity non-tangentially. So, Brian, this is a more complete answer to your question from yesterday.
Okay. So if your function, if your function is exactly of this type, then it is the function. It is the
Phi transform of some measure, of some infinitely divisible measure. But this tells you that for any mu, phi mu is approximately equal to something like this if you go to infinity inside an angle. Okay. Yes.
I'm sorry?
You said it was for this is your phi function. It's a
No, this is an arbitrary function.
oh,
But if it
Happens that if it happens that you have a measure mu such that phi mu is expressed that way in the entire half length, then mu is infinitely divisible and freely. Classically, no, but freely it's infinitely divisible. Yes, the convergence of such functions is determined basically by the convergence properties of gamma and rho. Strictly speaking, yeah, maybe. So in other words, a sequence of functions of that type, if you have gamma n's and rho n's, converges pointwise if and only if it converges, the gamma n's converge and the measures rho n converge weakly. Okay.
So now let's get back to the
Large numbers. So now Bn again are free identically distributed variables, but this time Bn are self-adjoint operators.
Unbounded.
And suppose that mu is their common distribution, which is an element in P. And let's look at the averages, An, which are B1 plus B2 plus Bn over n. And let's call mu n the distribution of this new variable An. So the question is, when does there exist a constant C such that mu n converges weakly to the point mass at C? Okay. So scaling and additivity of R. So that calculation I'm not repeating. Yeah. So you want to calculate the phi transform of this average. You use additivity and the scaling properties, and you're going to get that phi n is approximately given by
An integral associated
with constants gamma n and rho n, where gamma n is n times the integral of t over 1 plus t squared d mu of nt, and rho n is that measure n times t squared over 1 plus t squared times d mu of n. This is just calculation. It's not nothing very deep about it, but when do we have gamma n tends to have convergence to point mass? If you remember the phi transform or the R transform of a point mass. Here is the audience. What is the R transform of a point mass? A constant. So I'm interested when these functions converge to a constant. So in other words, the gamma n's have to converge to a constant, and the measures rho n have to converge weakly to the zero measure.
And this can be translated into the following two conditions. The limit of the interval from minus n to n, mu of t must exist.
So you see, mu doesn't have to have a finite moment.
But the moment
Minus n to n has to have a limit. And the second can.
Missing in that formula because that should be just the mass of minus n to n.
there's a t missing in that formula.
Thank you. Yes. Yes.
Right. You have to look at the
You see how the formula for gamma n has a t in the numerator. That's the t in question. Yeah. So if you change the variable so that nt turns into t, that's going to be the integral of t over 1 plus nt squared times d mu of t, and that will converge roughly. Will converge to the mean, to the expected value of t relative to d mu of t as n goes to infinity, provided that such an expected value exists. But if the unexpected value does not exist, then that sequence gamma n has a limit if and only if the integral of t d mu of t from minus n to n, thank you, from that has a limit.
and
And the second condition that the measures rho n tend to zero amounts to the condition that the limit as n goes to infinity of n times mu of outside the interval from minus n to n is equal to zero. And those of you who took a recent course in probability theory should recognize those two conditions, because there are exactly the conditions that are necessary and sufficient for convergence to zero
of the averages, or converges to a constant, I should say.
of averages in the classical weak law of large numbers. Exactly the same conditions obtained in this case. In other words, we have an equivalence between the distributions that give you something convergent in the classical case are exactly the ones that give you convergence in the free case. This is the upshot of this little calculation. Yeah, so that's so this is something that Pata and myself observed sometime. Actually, this is historically speaking, this came after a result of Pata, but I put it in this order because this seems to be the logical order. But what I had asked him to do is to look at the central limit theorem. So the central limit theorem, of course, you know the Voiculescu result, which is formal result, moment result. The question was, when is it true for unbounded variables? And what he found is that the conditions that obtain in the free case are exactly equivalent to the conditions that obtain in the classical case. So that was Pata's results. And after that, we thought, well, how about take a look at something simpler than this, the central limit theorem, which is the weak law of large numbers. And turns out that again, it's exactly the same answer. Yeah. We didn't know that magic formula at that time, so that's something that. Yeah. So and turned out that this is a part of a much more general result, which is this. Suppose that so first a definition. Suppose that you have a sequence Bn of free identically distributed random variables with common distribution mu, and you also have a sequence of numbers that goes to infinity of integers k1, k2, kn, and you denote by an a kind of average of these variables. So you take the sum of b1, b2 up to bkn. Notice it's not n. Could be more than n. It's at least n, but could be more. Multiplied by cn and add a constant dn. And let's say that mu n is the distribution of an. It might happen that these distributions mu n converge to some measure mu nu. And in that case, you say that mu belongs to the free domain of attraction of the measure nu. Okay. So the weak law of large numbers tells you that some measures gives you a characterization of those of the domain of attraction of a point mass. And Pata's result gives you a characterization of the elements that are attracted to the semicircle law. And of course, the same definition can also be given in the classical. In fact, that's where the concept first appeared in the case of the classical convolution of measures. So you can define classical domains of attraction on the line, and then this is what we managed to prove in the end, is that the free domains of attraction are exactly the classical domains of attraction. So it's not only for the law of large numbers and the central limit theorem are not an accident. They are just something that happens in complete, in much greater generality. And the result has been improved in various ways. So there are related results to about non-identically distributed sum n's. Okay, so that extends to that case. That's a result of Chistiakov and Goetze. I did that a little bit later. Yes, yes, those are the two cases that I have already discussed. Now, superconvergence. That's another little phenomenon that happens in the. So this is a situation in which you get something a little different in the free case than in the classical case. So let's say that Bn are free identically distributed. So the distribution tau of B1 is equal to 0, tau of B1 squared is equal to 1. So the central limit theorem applies. So B1 plus B2 plus Bn divided by the square root of n. There's a distribution mu n that converges to the standard semicircular law. And if you remember, the standard semicircular law is an absolutely continuous measure, supported interval from -2 to 2. And turns out that for large values of n, mu n is also an absolutely continuous measure. It's supported an interval alpha n bn that looks very much like the interval from -2 to 2. And the densities of mu n are analytic and converge uniformly to the semicircle density on the interval from -2 plus epsilon to 2 minus epsilon. And the truth is that you get uniform convergence. I think J.C. Wang actually proved that you have uniform convergence everywhere. It's, including at the. That's not so surprising, but it's good to know. So you have uniform convergence on the entire domain. You just don't have analyticity at the endpoint. So this is a result that that Voiculescu and I proved some time ago. Yes, and the analyticity at the points alpha n and beta m, of course, don't hold, because this distribution really will look like a semicircle. So it will hit the graph, the density will hit the real line shape, a 90-degree angle from a certain point on. So that's the situation there. So let's see. Now this result was eventually extended to all free domain of attractions. So this is work that J.C. Wang and our host, our gracious host here, Ping, and myself have very recently. And this even extends to non-identically distributed summands. So whenever you have a limit of this type to something that necessarily has to be an infinitely divisible measure, actually you have uniform convergence, analyticity and uniform convergence of the densities on the proper domains. One has to qualify it a little bit because an arbitrary infinitely divisible measure is not might have a point mass, might have 1 point mass. So of course you don't expect densities to converge at that 1 point mass. But other than that, you have uniform convergence. I'm not going to prove it. This is not part of the program today. Okay. Here comment about large deviations. And what follows. Maybe I should have said something else which I forgot, which is why is this a little different from the classical case? The probabilists, of course, will know immediately what's very different about it, and what's very different about it is that in the classical case, you know, the measure mu that you started with could have been, let's say, classical point toss, the Bernoulli variable. Right, Bernoulli variable, and you add n Bernoulli variables, you still get a discrete variable. You never get something analytic. You don't get densities. Nonetheless, the limit, which is the Gaussian, does have a density. So, but certainly, you cannot say that the densities of the partial sums of the weighted sums converge to the density of the limit because they don't exist, those densities. So in some sense, this is a little better. So this is a phenomenon that seems to be happening quite a lot. That results that have analogs in the free case, the results of classical probability that have analogs in the free case, turned out to be a little better in some way than the classical one. Yes.
Are there examples if I just have two? If I just have two measures that are, say, not delta measures, and I take the free convolution, is that necessarily absolutely continuous, or are there examples where you can have?
Yes, essentially it is true. It is true. This is a result that Sherban-Belinsky proved. So it's essentially true in the sense that the free convolution might have a finite number of point masses. But other than that, it's absolutely continuous. I will discuss this. I was planning to talk about this either Wednesday or Thursday. Wednesday, Friday. Friday, I will get to that. But yes, that's a general. So the absolute continuity happens right away. And the atoms disappear also pretty quickly in this.
Okay, so
A little point about the large deviation. So what's meant by large deviations? If you have, so again, suppose that I have the same setup that I had a moment ago. I wish I had not made these mistakes. Yeah, okay.
I'm not straight.
You see, I had 2 years to prepare this presentation. So I kind of just kind of lost in the midst of. So who knows when did I write this? Maybe it was 5 months ago or something. But it's right. So take some bn's which are in the setup of the standard central limit theorem. So the averages A1, the weighted averages A1, AN, which are the sums, partial sums divided by the square root of n convergent distribution to the standard semicircular law. So if you divide them by a further square root of n, AN divided by square root of n, that's law of large numbers. That's going to tend to 0 in distribution. Okay. So what is meant by a large deviation estimate? Well, you look at the probability where AN over the square root of n is bigger than epsilon. And this has to go to 0 because point mass, right? How fast does it go to 0? Well, the support convergence tells you that if it's something here, yeah, at what rate? At what rate? So in the classical case, what you have in for good probability measures, for good initial distributions, mu is you have an exponential rate, which is given by an entropy function. So what happens in this case? So this theorem, the superconvergence theorem, tells you that actually the probability that AN over the square root of n being bigger than epsilon is in fact equal to 0. So converges to 0 very fast indeed. It's a little disappointing perhaps, but that's the way it is. So however, if mu does not have bounded support, then one might get a theorem. So let's say that let's say that your measure mu that you started with is Gaussian, classical Gaussian, right? So the support is unbounded. You take the averages, even if they are free averages, they are still going to be unbounded random variables. So one should be able to estimate this kind of thing. And I don't know that anybody knows for that. I mean, it should be better than exponential, right? So but you know, there should be again some kind of entropy functional that tells you at what rate this goes to 0. So if the support is equal to 0, then entropy is infinite. So there's nothing that you can say about that. And now this turns into a pattern there. So I have that number 2 at the bottom, and I guess I spoke faster than I meant to, because that's supposed to be the end of today's lecture. But I will make some more comments just so that I use up my time. And yeah, so this is all in the large deviation. What should I subculture? It's called the level 1, I think. It's a level 1 large deviation. So it's a large deviation for processes that tend to on the line, basically, right? So you have processes that happen on the line, and they tend to a point. And the question is how fast, how can you estimate how far you are from that particular point? Yeah. So those are the large deviations. But there are other processes that one could apply this kind of reasoning to. So another standard example that comes from let's say Boltzmann considerations of a Boltzmann model for. So in the Boltzmann model, you've got of it is that you've got n particles. Yeah, you have n particles, and each one can be in a finite number of states. So let's say you look at the molecules of oxygen in this particular room,
and we divide the room into a number of pieces, and each molecule has a certain probability of being
this piece or in that piece, and so on and so forth. Yeah. So you have a number of states. So there's a state space for each molecule. The state space is the same. And having n particles means basically that you look at the n-fold product of this particular probability space. And an element in this particular space is what one might call, so to give an element of this space, basically means that you have indicated for each particle where it is.
which state that particle is. So it's what this is something that might be called a microstate. It's a microscopic
Description of the system. So you know exactly where each particle is. Particle 1 is in this room, particle 2 is in this one, and so on and so forth. But there is also a macroscopic state that you can extract from this microstate, which is you can count how many states, how many of the particles are in state 1, how many are in state 2, how many are in state 3, and so on and so forth. And this gives you
a probability measure on the state of space.
On the space of states. The state space. A probability measure which depends on this. That's the macro state that's associated with this particular. And then there is a law of large numbers in this particular case, which says that the macro states, as n goes to infinity, the macro states will approximate very well the probability distribution that the probabilities that you have for the various particles to be in the. And the law of large deviations is so in this case you don't have a limit which is a number, but it is a distribution. And the large deviation estimate amounts to looking at what's the probability that the microstate is far away from this state. And again, this probability is estimated asymptotically by
an exponential rate given by a certain rate function, which is essentially the
Boltzmann or the Shannon entropy of the well, so let's say that you want to know what's the probability that you are close to some other given distribution, which is different from the given the initial distribution on the probability space. And yeah, so well, let's so the probability that you're close to a given microstate is something which is proportional to e to the minus n times the entropy of that particular macrostate. And this is essentially, this is not the way that Voiculescu presents it, but this is perhaps a more convenient way to understand what the free entropy, what the notion, how the notion of free entropy arises, right? So because so there's this
process
that we know. It's the Wigner process, right? The GUE. So for each n, you take xn, which is the
GUE normalized so that
the variance is equal to 1. And we know from Voiculescu that this tends to.
So again, we have, or another way to put it is that once you give yourself a
yeah, so you have another situation in which you have a limiting process in which the limit is not a point on the real line, but it is a measure. You can ask again, what's the probability that you're falling away from that away from that particular measure, and the entropy is precisely the rate function at which this happens. Okay, so you have some other probability distribution, and you want to know whether you're close to that probability distribution. It turns out that that probability is of the form, or approximately e to the minus n squared this time instead of n, e to the minus n squared times some sort of entropy function. That's the okay. So maybe this was a worthwhile addition, and maybe not. But I'll thank you here. Thank you for your attention.